Awesome. All right. Hey, guys. Welcome to Experiment 5 review. Today we're talking about thin layer chromatography. So first off, I want to just address your Experiment 3 and 4 worksheet grades. I've only looked at a few of them so far, but they look decent. It seems like my point really got across in the last video, which I'm very proud of. I just finished grading and reporting grades for the Worksheet 1 report, our assignment. Most of you did extraordinarily well. I'm very proud of all of you. Some of you that did struggle, it were just some minor technical issues, meaning like confusion between definitions of expected versus recovered, and what excipients/binders are. Just to retouch on that for 1 second, I will say one more time, the excipients/binders are not the active ingredient. And remember, your active ingredient is your ASA in that situation, the acetylsalicylic acid. And this is important because it will come up again. And as you can see, ASA is another example being used in today's lab, Experiment 5, the TLC. So as you noticed, I labeled the thumbnail for the video for TLC Experiment 5 on my YouTube channel as Tender Love and Care. That's what it is, that's what we got, and that's what we're looking to embrace today. Tender love and care, nothing but. I did notice that on the last video when I rewatched it, I am extraordinarily sorry, and I apologize, because I realized, I don't know what I was thinking. I had known this before, but the expo that I write on the whiteboards, it shows up backwards and it doesn't show up very clearly. So it's hard for you guys to understand. So I've taken that into account and I plan to address it this time around. The diagrams I put on the whiteboard are readily available visually throughout the entire video. So unfortunately, the worksheet for Experiment 5 is pretty much all multiple choice. So for me to share my screen and then go through it question by question would just be giving you guys every single answer. To avoid that, I'm going to try and avoid sharing my screen and just share with you right now my opinions going from each question to each question. Heck yeah. One moment, guys. All right, here we are. So for this experiment, actually, the first question is a little bit based on the concept of the chemistry involved. So I'll actually touch upon the procedure first of all, because I know it's an hour-long or close to an hour-long video for the lab experiment, and you guys, have better things to do with your time. Well, maybe this is pretty cool, I think. But to get the point across is TLC. It separates compounds from other compounds based on their polarity. So essentially, what you do is, say you have a compound that, and I'm going to give you guys arbitrary numbers here to try and understand. So say you have a compound that is arbitrarily 75% polar, okay? 75 out of 100% polar. Then you have another compound that's 25% polar. But they're both organic, they both dissolve in the same solvent, you have both of them in methylene chloride, and you take your IR, as we discussed in the previous lab video, the infrared spectroscopy, and they show up pretty similar, and you can't tell the composition of one to the other. And we're not going to use gas chromatography or refractive index here because perhaps one of them does not change states from liquid to gas as readily, so you can't use gas chromatography, and you couldn't use refractive index perhaps because perhaps these compounds have a certain degree of solubility. So they're not 100% soluble in a certain solvent, so the refractive index is a little less reliable. So what we're going to rely on today is TLC. And fun fact, most of you are PharmD, and a lot of you want to go into research, and something that researchers, scientists, physicists, chemists, biologists, PharmD majors who end up in any of those fields do numerous times every single day is the TLC, the thin layer chromatography. And it's called thin layer chromatography because you use an aluminum plate with a very thin layer of silica gel upon it. Now, in other forms of chromatography, you'll use silica gel as a powder, and you'll pack it into a column or something otherwise, and you'll push your compound through, dissolved in a certain solvent. And I'm going to go into the chemistry and go over that now. But the reason it's called thin layer chromatography is because instead of using a column or any other weird thing with a bunch of powder of silica gel, this is silica gel that has been treated directly onto the aluminum. So when you purchase it, it comes in a cardboard box just with like little plates, kind of like sheets of paper if you're trying to replace paper for your printer, except instead of regular paper, you get aluminum with silica gel plastered extraordinarily evenly directly onto the plate. So moving on. The next thing you want to do is take your solid products. For example, we're using ASA and caffeine. I'm going to show you guys some drawings of their structures in a moment. But using, for example, ASA, acetylsalicylic acid, and caffeine, those two examples, they are both organic compounds. They're soluble in methylene chloride. So let's say we dissolve pure substances, or pure, as far as we're concerned, substances of those two compounds in methylene chloride, both of them. Then we take a small capillary tube, which is just a very, very, very thin layered tube, glass tube, where you just dab it, and the capillary action, aka the cohesive property of the solvent, pulls it up. So fun fact, adhesive means one compound's propensity or ability to stick to another different compound. So a heterogeneous combination here. Your cohesive ability is one compound's ability to stick to itself. So for example, with water, you have this highly electronegative, like electron withdrawing compound, oxygen, up here. And we know it's a bent shape, okay? So you have two more hydrogens down here. So we know that oxygen and the two hydrogens, they form bonds with other water molecules to make sure that each hydrogen has a partial bond between the hydrogens and the electronegative oxygens of other water molecules, whereas the oxygen has a partial negative bond with two other hydrogens of two other separate water molecules, per se. And even, I understand that is hard to imagine. So if you could please ignore what's already on the board now, and I will draw this here. Otherwise, I would have already had it put out. But I will have oxygen, hydrogen, hydrogen, okay? Oxygen's electronegative, meaning it has a greater propensity to attract electrons because it's closer to filling its valence shell than hydrogen, which is only one electron in its valence shell. So we know that if we have another molecule of water, it's going to interact like this. And I know it's very hard to see, but there's a solid lines between the O and the H and the H here, solid lines between the O and the H and the H here, so that way we know each water molecule 1 and 2, they have the same structure. This is a dotted line. The dotted line refers to the partial bond that the partially negative and the partially positive charge have to one another. And that's because oxygen has such a high electronegativity that it hogs electrons in this OH-H bond, and hydrogen is vice versa. It has less electrons. So even though they share electrons, the propensity for the electrons to be close to the oxygen is much greater. So you're able to form hydrogen-oxygen bonds within the water. And that's where you get those bonds. I'm going to put this down. All right. Now, to get you guys through this worksheet and to make sure that you do well and understand the concepts, the first question, and unfortunately I cannot share my screen this time around because all the questions are multiple choice, or most of them are, and to just share my screen would be to give you guys every single answer. I know you love that, but unfortunately it's not going to happen today. So, give me a moment to speak about polarity. First of all, a couple of the questions you're going to get right off the bat are which hydrogen in the given structural, all right, so you're given an organic compound structure, all right, it's going to be one of your following, your ASA, caffeine, ibuprofen, acetaminophen, or naproxen, and they're going to highlight certain hydrogens. They're going to ask you which one is the most acidic. Now, in order to determine this, you have to look at the different functional groups they're attached to. and the different atoms they're attached to, and consider their electronegativities. So, for example, now I will share my screen with you for a moment. Give me a second. Share. Awesome. Oh, so to go from here, electronegativity. So we know that electronegativity moves in this direction. I hope that's congruent with the direction of the arrow in the video, even though it's reversed. Otherwise, it's that direction. However, the picture shows. Anyhow, from the bottom to the up, it goes for electronegativity. Now, the definition of electronegativity, if you can see on the screen here, is one atom's ability or propensity to want to grab an additional electron and add it to its balanced shell. Now, why do we think as chemists, why do we think that an atom would want to steal an electron and add it to its valence shell? To complete the valence, because we know when an outer valence shell is completed, we have an extremely stable molecule, and that's what we're always trying to achieve, and that's what atoms are always trying, that's the state that atoms are always trying to achieve, the most stable energy configuration. It's that full valence shell. So we know that our electronegativity increases an upward to the right curve when we look at the periodic table, because we want to fill all of those halogens, the second from the most right column, we want to fill all of them with one electron to complete their outer valence shell. So we know that, for example, fluorine is the most electronegative. So you add one to that, it has the same configuration as neon, although since the protons in the nucleus of the atom did not change, you still have fluorine, but you have a more complete valence shell, etc. So I stopped sharing my screen, and now I'm going to move on to other questions. Alrighty. So the first few questions that I see have to do with whether or not hydrogen atom, or which hydrogen atom is the most polar. So I'm going to have to address this with you guys now. I'll tell you that ChemDraw will help you greatly. And if you can't get it, don't worry. But I will demonstrate it very quickly right now. Sharing my screen again. Bam. So ChemDraw is something that you can download. I had a lot of students ask me about this the first worksheet, and I wish I had given more demonstrations for the second and third video I had given, but you know, that happens. Anyways, I'll demonstrate it here. So as a result, here you see my mouse. I'm going to go down and click on my CD little app here that I attached to my icon bar. Again, this is ChemDraw. I think the latest version is 16.0, and it comes with the school if you're a student from the school. All these little bars I have around here are little view menus that I opted, like I chose for my specifications to have available. Now, something I would like to point out is that when you click view, you can show the structure toolbar. All right, so I just clicked that and it went away. It was right here above my periodic table that you guys can see. And I'll click it again, share one more time, structure toolbar, beautiful. This is an important feature because it allows you to go from name to structure. For example, if I click on name to the pointing arrow to the hexagon, and that hexagon, by the way, is benzene, I'd just like to point out, then let me just go here, type in Acetaminophen. Let's hope I typed that out properly, and I did. And here we see Acetaminophen. Exactly as it should look. So we have, and this is the most important part of this entire lecture, because most of your questions do pertain to the polarity of certain functional groups. So here I'll point out this, which I've highlighted, is an amide. So an amide is essentially an ester. So a carbonyl, aka a C double bond O, adjacent to a C bond O, that's an ester. But to switch it to an amide, you have the same exact situation with the exception of an amine. And the amine makes it an amide. It makes it what it is. And when you're looking at certain questions, for example, what I have here, which I have highlighted, is a primary amine, meaning that the basic description functionality to become amine means that it must be attached to a carbonyl carbon, meaning it must be attached to a carbon that is attached to has a double bond directly to an oxygen. So here's your amide, okay? So coming off of here and here could be any compound or combination of atoms, etc., as long as they fit properly. The amide is strictly a nitrogen attached to a carbonyl, which is a C double bond O, okay? And now to call this a primary amide would say that it is the nitrogen, the N, is combined to one carbon. Now to call it a secondary would be this. Now it's a secondary amide. And to call it a tertiary is non-existent, because what do we know about nitrogen? Nitrogen can support only 3 bonds. Yes, we know this. And as a reminder, I'll just demonstrate right now using ChemDraw, because ChemDraw likes to point out all these little tidbits. We have HONC, H-O-N-C, the 4 most important elements to organic chemistry. And when I click on hydrogen and display it in ChemDraw, it automatically shows up as HH, 2 hydrogens. That's weird, right? Why wouldn't it just show up as a hydrogen atom, a singular one, with no friends or whatever? I don't know if you like that, friends, but. And same oxygen, oh, it showed up as an H2O. That's pretty obscure. Now, ChemDraw has certain methods to deliberate certain elements and explain their polarities and electronegativities in an explicit way. But oxygen is also similar to hydrogen in the way that if you found atomic oxygen, it would be attached to another oxygen atom. It would be O2. Now let me click on carbon, see what shows up. Oh, we have a CH4, the most common singular carbon molecule, methane, CH4, and nitrogen, so NH3. So from this, we can see what I said before and what you learned last year, HONC, H-O-N-C, all right? So hydrogen, 2 H's, oxygen, OH2, all right? And let me just point out one more time, the reason it's 2 H's is because this is the most abundant form that you find atomic hydrogen, or the closest form to atomic hydrogen that you find it the most abundant way in the universe as diatomic hydrogen gas. Same thing for oxygen. It's most abundantly found as water, so you have H2O. And same thing for carbon. It's most abundantly found as CH4, so you find methane, CH4, and nitrogen, which can only make 3 bonds. So it's most abundantly found as ammonia. We call NH3 ammonia. So HONC, H-O-N-C, we know because H can only form 1 other organic bond. O in the HONC can only form 2 organic bonds. N in the organic HONC can only form 3 organic bonds, and carbon can only form 4. Alrighty. So moving on, I'm going to stop sharing my screen for just one moment, guys. Actually, I'd like to touch more upon these functional groups before I move on. First of all, you guys probably won't be able to read this, but this is mostly for my reference. I've understood now, unless I bring it extremely close to the screen. Alrighty, so first of all, I have ether written up here on the board. So to describe, I want to describe explicitly what each of these functional groups mean, because you guys will need to know in order to succeed on this worksheet. And you also need to know their polarities, not just their structures. It's not hard, it really isn't. I'll make it as simple as I possibly can. Okay, so in this understanding, ladies and gentlemen, we have here an example of an ether. So we have O bonded to some other group, bonded to some other group, all right? So whenever you see R represented, that just means any sort of organic group that fits the electron model could possibly be there. It's just an arbitrary variable to explain that this is what the group looks like. And it's the easiest way to explain it. So I will be using R to reference different functional groups from here on out. So this is what an ether looks like. And now to describe a carboxylic acid, I'll draw that for you now. We have here a carbon bonded to 2 oxygens, okay? A double bond to oxygen and a single bond to oxygen. And then here, what do we have? As you guessed, an R. So we have an acid. What do we call this? A carboxylic acid. C-A-R-B-O-X-Y-L-I-C, carboxylic acid. So here's an acidic functional group. And I'll explain the difference between any other functional group and acidic functional group momentarily, because that's crucial to doing well in this worksheet. Moving on, I'll describe another functional group for you guys, the amide. In order to do so, I'm going to copy and paste the carboxylic acid and use this to demonstrate to you what an amide looks like, because we know this is an amide. An amide is literally a carboxylic acid with a nitrogen. So the only way in which they differ is by their electronegativities, and you can infer that based on the electronegativity chart of certain atoms. As we can see, here's oxygen, here's nitrogen. Oxygen is to the right of nitrogen, even though they're in the same row. So we know oxygen is more electronegative than nitrogen. So we're able to infer, that a carboxylic acid is going to be more acidic, meaning it can give away its proton, than an amide, and I'll explain that more deeply soon. I know that was a very brief explanation. I'll give a very deep explanation for that in a moment. But moving on, an ester I want to demonstrate is going to look like this, right here. So an ester is literally a carboxylic acid with another carbon coming off of its hydroxyl group from the carboxylic acid. So we're going to back up from that for a moment. And also, let me just point this in your head. What do you think would be more acidic, carboxylic acid or an ester? I'll let you think about that one, answer it. But here's a hint. Think of the electronegativity of the oxygen, aka the stability of the oxygen's outer shell when it's sharing electrons, or the dipole, meaning the concentration of negative to positive charges in the bond itself when oxygen is bonded to carbon as opposed to hydrogen. Because remember, oxygen is so electronegative, it draws so much of the electronegativity, the electron's polarity, their negative charge, towards it, as opposed to hydrogen, which is kind of the opposite, completely opposite, to be honest, because it's only a one electron atom. So now you have a hydrogen, a singular electron atom, attached to an oxygen, an 8 electron atom. It has an incredibly high electronegativity as well. So even though they're sharing bonds because they're in a covalent bond, the oxygen is going to hog most of it. So maybe if you calculate the average percent of the time the electrons spend on the oxygen side as opposed to the hydrogen side, maybe you'll get like 70 to 90%. So that's why the oxygen hogs negativity between the two dipoles. And that's what a dipole is, a difference in charge, the negative to the positive, aka the oxygen and the hydrogen, because the oxygen is more electronegative and the hydrogen is less electronegative. So there we have esters. When you add a carbon, the carbon is less or is more electronegative than the hydrogen, aka less of a difference of electronegativity between the oxygen and the carbon as opposed to the oxygen and the hydrogen. So you're able to achieve a more stable bond between the two atoms. So that way we know that an ester is less acidic or less reactive than a carboxylic acid. Moving on, we have alcohols, and I'll demonstrate that right here. So we have an O bonded to an H. And I just hit Z right there because I accidentally hit something incorrect. Whoops. Capital R, enter. And here, bing, bong, boom, we have an alcohol. So anything coming off as an OH, that's an alcohol. And the importance of alcohols is that they're ionizable, so you can remove that hydrogen from them. So they're somewhat reactive, and if they're bonded to certain compounds or functional groups, they're highly reactive. So we have ROH. Moving on to the last example we have here, and I'm going to actually just modify the alcohol example. Bam. And notice how it went from ROH to RNH2, because as we just discussed, you have HONC, H-O-N-C. 1 bond, 2 bonds, 3 bonds, 4 bonds. So O has 2 bonds that it can stabilize, and N, nitrogen, has 3 bonds which it can stabilize. So a nitrogen, an amine, we call it an amine, is bonded to anything else. This is the R group, so it could be car or whatever. Any other molecule, 1 bond is the important part to remember. It will have 2 hydrogens bonded to it, because in order to be stable, it needs at least 3 bonds among its core, the nitrogen core. So now we have an NH2. Now, in order to make this a secondary amine, you might add something here. We'll call this R as well. And now we have a secondary amine, okay? Now, same thing can be converted to this amide that I described previously. Right now, we have a primary amide. Let me make it a secondary amide. Bam. Let me make it a tertiary amide. Bam. Now we have 3 bonds connected to the nitrogen. We call that tertiary, and that's the maximum bonds it can take. Let me try and put an extra one there, even though it can't sustain it. Bam. We got a little red flag. That's because HONC, H-O-N-C, 1 bond, 2 bond, 3 bond, 4 bond, hydrogen, oxygen, nitrogen, carbon. So, moving forward, stop sharing. Alrighty, 1 moment, guys. Hopefully that helps you guys decide the difference between acidity. If it didn't, let me tell you this. Acidity is described as the propensity of a hydrogen atom, aka a proton, meaning a hydrogen atom without a neutron, just a proton and electron, or just a proton to be honest, a hydrogen proton. The propensity for it to leave the molecule's core. So when we have an acidic compound, the electronegativity of the oxygen plays such a significant role that it draws so much of the negative charge from the carbon, it really doesn't need that extra hydrogen attached to it, attached to the external oxygen, to sustain itself. So let me give you guys an example. All right. So, all right. Here we have ASA, but I'll just reference this, carboxylic acid. So here we have a carboxylic acid, okay? We know the electronegativity of the oxygen is incredibly high. So for here, we have a partial negative charge of the oxygen, partial positive charge of the carbon, because it's a carboxylic acid, and this is much highly more electronegativity charged than the carbon. And same for the oxygen. The hydrogen has such a low electronegativity, it forms a dipole, aka this is significantly, and significant is the key word here, significantly more negatively charged than the hydrogen. So it is able to lose that charge and maintain a stable negative ion charge with the oxygen here. Now, let's say we lose this hydrogen to any circumstance, all right? And this is an acid, so it can easily lose its hydrogen. We put a minus sign here. And I know I don't have my Excel marker, but let's just imagine a minus sign there, because that would form a carboxylate. Now, the difference between a carboxylic acid and a carboxylate is that a carboxylate has charge. So it will have a negative charge because the hydrogen is not there, but is able to stabilize it because of the electronegativity difference between the carbon and the oxygen. And moving on, let me just check on the next question so that I can make sure I'm answering all of your proper questions. Now, the next several questions actually, beneficially to you, have to do with the calculation of the RF value. Now, the RF value is a very easy calculation as opposed to trying to determine polarity of certain compounds. And the RF value has to do with, okay, how far did my compound travel as opposed to how far could it have traveled?